NED Library, absolutely autonomous education. We are technocrats, astute entrepreneurs, and above all, passionate academics. We are education specialists, rendering learning solutions to schools, corporates, and government, such as a broad spectrum of digital learning environments. We are the bridge between students and teachers. Our role is complementary. Our focus area is the curriculum, how well suited it is to the industry's skills demands. Reading seemingly is a handicap. How well adjusted is the content to fit to the target audience? There is always a way for a fish to willingly take the bait.
Earlier, we had alluded to the fact that photosynthesis is a process whereby light energy is converted into chemical energy. And from the law of conservation of matter, I understand that you know that you can neither create energy nor destroy it, but all that can happen is that energy changes its forms. So you realize that in terms of energy, there's what is known as, it exists in two states. That is the free energy, and the heat energy. Free energy speaks of the energy that is available for an organism to do work, and heat energy is what is eliminated as what you lose as an organism is doing work. And I want for us to focus on it's not really the definition, but sort of a statement that explains what happens during the process of photosynthesis. And as you can see on the board, I have written down some of the keywords that we're talking about. That is photophosphorylation and photoexcitation, and we are trying to marry that with the definition that we have given for photosynthesis. We have said that it is a process whereby our light energy is converted into chemical energy. So we want to see how our light energy is doing it, and what is we need to know what our light energy is and what our chemical energy is from what we have alluded to earlier on. And you realize that our light energy is referring to the issue of photoexcitation. And when we talk of chemical energy, we are talking about photophosphorylation, because you remember from light energy, photoexcitation, we are talking about, these are electrons. You shall soon get to realize how it works. And then as we're talking about chemical energy, what we touched on earlier on were those molecules such as your N, A, D, P, H. This P is referring to your phosphate, and we've spoken about ATP. This is the chemical energy that we're talking about, which is more stable and which can be used in terms of when the sunlight is scarce, like days which are rainy. And before we get into the intricate details pertaining how the whole story unfolds, let us consult our PowerPoint so that everything gets to sink in. So according to our PowerPoint, we have looked into the following: the site for photosynthesis, the stages for photosynthesis, and we've realized that there's the light-dependent stage and there's the light-independent stage that is known as the Calvin cycle. And then we have realized that chloroplast is suspended inside the cytoplasm, and it is the site for photosynthesis. And we need to understand what kind of a structure a chloroplast is. And as shown by the picture, you can realize that it is a double membrane structure. These are two membranes. And what we have here is the magnified view of, because we're talking of a structure for, what is this? The structure for the chloroplast. This is the membrane that you have for your chloroplast. But in this, at the same time, we are also looking at this structure, which is your thylakoid. Like I said, thylakoid is made up of your grana. A stack of your grana is made up of 3 thylakoids. But now when you look at it, this is the magnified view of the membrane of this structure called the thylakoid. And as you can see, we want to talk about the membrane. The membrane is made up of biphospholipid structure. It is a biphospholipid structure. And what we mean by biphospholipid structure, meaning it's got 2, these are 2 layers. As you can see, you have got this is your head, the head of your membrane, and the tail, and the other side is the head and the tail. And it is the head of your thylakoid membrane. In fact, all the membranes are like that. What you have is the head is made up of phosphate, and then you have your tails made up of lipid. These are fats. And we know that as far as the characteristic of this in water, a phosphate is soluble in water, but a lipid is insoluble. So you realize that the heads are said to be hydrophilic, whilst the tails are said to be hydrophobic. Phobic from the word phobia. And you realize that right on the membrane, there are proteins. There are protein structures that are found there. As we go deeper with the presentation, we shall get to realize how they work together. But as far as a membrane is concerned, you realize that membrane is about maintaining a certain environment in the cell. How do we maintain that kind of environment? The environment is maintained by means of allowing some substance into our internal membrane, whilst disallowing some of the substance into our internal membrane. So we move on to the issue of the stroma. We have covered that. Thylakoid contains chlorophyll. We covered that. Let's move on to the next slide. Okay. So now what we are going to do is we are going to be looking into detail, like from the previous slide, you realize that this is the structure that we are talking about. We just cut through a small portion of your thylakoid, and we are looking into the membrane, not inside of your thylakoid, because you realize that the thylakoid is a structure. It has the thylakoid membrane, and inside your thylakoid as a structure, there's what is known as the lumen, and we shall get to cover the details shortly. So what we are talking about right now is what are these tiny guys that we see on our membrane, the membrane of the thylakoid, and what are the functions. And what we are covering right now is the details of the light-dependent reaction. So in other words, what we are trying to explain is the issue of those keywords that we have covered, such as photoexcitation, such as photolysis. It's gonna be explained by these structures that are found on the membrane of the thylakoid. And according to the presentation, let me just read out what is there. You realize that a thylakoid, it is a membrane-bound organ, and the membrane separates environment, like what I've already alluded to, by allowing certain molecules and ions in, whilst disallowing others. And inside the membrane is the thylakoid lumen, and you'll understand that relatively large molecules and polar substances require protein transport channels. And maybe wondering what we're talking about when you say relatively large molecules, but I think this one is self-explanatory. Maybe you might be wondering what we mean by polar substance. If we're saying something is polar substance, so we're talking of a molecule which contains, be it a positive or negative negative end, you'll understand that properties of a membrane, plasma membrane, it is, some say selectively partiable, some say that it is semi-permeable, some say that selectively partiable, selectively permeable, semi-permeable. All these phrases are just but referring to one thing, meaning that the membrane is designed in such a way that positive polar molecules cannot permeate, cannot cross over from one environment into the other. So this is what we are going to be talking about, because you realize that we have touched on the issues of a molecule such as ATP. We have touched into a molecule such as NADP plus. As you can see, this is polar, and also NADPH. So you realize that we need to touch on the issue of transport before I get to explain the intricate details regarding our membrane. You will realize that as far as transport is concerned, we are talking about active transport. Molecules move from one environment to the other through the means of active transport or passive transport. Under passive transport, we are talking of things such as, processes such as simple diffusion, you are also talking of processes such as facilitated and you are also talking of processes such as osmosis. All this is what is known as passive transport. Of main interest as far as photosynthesis is concerned is the issue of, for now, let's narrow it down to the issue of passive transport. You realize that as far as one term that we are all familiar to is the issue of simple diffusion. And when you talk of simple diffusion, you realize that it is the movement of molecules from a region of their higher concentration to a region of lower concentration, down the concentration gradient. And when you look at it, it's more or less the same as when it comes to the definition of osmosis as well, because they are saying that osmosis is the movement of water molecules from a region of their higher concentration to a region of their lower concentration, down the concentration gradient. But now the distinction is in the issue that as far as osmosis is concerned, in order for it to happen, what we require is a membrane, partially permeable membrane, But when it comes to simple diffusion, diffusion happens with or without the membrane. And this is the concept that we are going to be explaining as far as these guys that you see located on the membrane are concerned. So before we fly off the handle, let's take it slow and nice through our PowerPoint presentation. So let's talk about our transport protein on the membrane. So like we said earlier on, we have touched on the issue that our membrane is made up by, it's a layer which is made up of phosphates and lipids. But at the same time, there are these guys that you find embedded on the membrane, and these are protein channels. These are protein channels which are responsible for transport. Actually, we call them protein transport complexes. So we need to know their names and what they do. So the first one that you encounter on the thylakoid membrane is what is known as photosystem number 2. This one is photosystem number 2. And what we have, like if you notice, you have got this line that is moving through until we get to this molecule called the NADPH, which I said is a molecule which is responsible for carrying our electrons, rather harvesting our electron, which we need for the energy generation, our ATP generation. And then also, when we move on to this line, this path, we're moving on to this way, and then we end up with our ATP there. Okay. So what we're talking about is there's a certain substance that is moving through these channels and is being relayed by some certain molecules. So you realize that there's a protein transport which are responsible for transporting substances. But now what we have in between are electron transport. They are specifically designed so as to carry electrons until they reach their final destination. So what we have on number 1 is shown by our presentation on our PowerPoint. Is this structure here is called photosystem number 1, and we shall get to see and understand how it works as far as photosynthesis is concerned. And then what we have here is a complex which is known as Cytochrome BF complex. And then this one is our photosystem number 2. Number 1, this is photosystem 1, and this is photosystem number 2. And this channel is known as the NADP plus reductase, and we shall get to understand what it does. And then the last structure that we have on the inner membrane is known as the ATP synthesis. And I understand that from the subject enzymes, whenever you get the yes at the end of a name, it's pointing to the issue of an this is an enzyme. And it is involved in anabolic reactions, and we shall get to know what that is all about. And then, we shall also touch on the issue of what the sour Q is. Some of the names are interesting to pronounce, so I'll just let you out read out on your own. So we're talking of our Q. This is our electron. It carries electrons and passes it on to our complex. Then from our complex passes on the electron to another electron carrier, and then it's passed on to another electron carrier known as FD until it reaches our molecule NADPH. And before we get there, we need to understand exactly what is going on with the issue of electrons. Why are they important as far as the process of photosynthesis is concerned? Okay, let's consider our molecule NADP plus, and as alluded to earlier on, we have realized that this is the oxidized state of NADPH, which is the reduced state of this kind of molecule. So what exactly happens? So in other textbooks, you realize the equation that goes on like this: NADP plus, meaning that it has lost an electron, and then you get plus H minus, that will give you the molecule NADPH, which is the end product of a light-dependent stage of photosynthesis. And then at some other instances, you find the molecule, the equation expressed in such a way, you've got NADP plus, and then you got 2 electrons plus a hydrogen, giving you the NADPH molecule. And in order to really understand what is going on, it is important for you to understand the configuration of our hydrogen molecule. So you'll understand that we have got this. It fills up of 2 electrons, right? And it has one proton. So this is what happens when our hydrogen atom, when it gains an electron, gain of electron, it ends up as H minus. And when it loses an electron, it ends up as H plus. So in terms of the number of electrons here, when it is a minus 1, it has 2 electrons, it's got 3 electrons. So what we are talking about right now is, like, look at this stage. This H minus is the same as 2 electrons plus your hydrogen cation. How is it that we are saying that in order to get to a stage like this, whereby we've got our hydrogen anion, this molecule initially has to gain, when it gains 1 electron, at first, like when you're looking at it, the state it has lost an electron. When it gains 1 electron, what we have is your hydrogen atom. And then when you add another electron, what we have is your hydride, that is your hydrogen anion. So this is what is going on. So as we go into the intricate details of photosynthesis, these 2 equations can be used interchangeably, just depending with the scenario at hand. So there's no need to get confused about it. So we can move on. Let's talk about photosystem number 1. Photosystem 2, the first one that we encounter, and then you get to cytochrome complex, cytochrome B6F complex. Then from that complex you move on to photosystem 1, and then you get to NADP reductase, and then finally what you have on the membrane is ATP synthesis. Okay, so as you can see, photosystem 1 and photosystem number 2 and photosystem 1, from the image, you can see that these 2 structures are responsible for capturing our energy, our light energy. And from thermodynamics, we realize that light travels in packets of energy that are known as photons. So the photons are the guys responsible for photoexcitation. So you realize that later on I'll get to show a slide of the structure of chlorophyll. You realize that their electrons are trapped within our chlorophyll, and the chlorophyll is found both in your photosystem number 2 and your photosystem number 1. Of course, there are differences between these two structures, and we shall get to delve into it later. But as for now, the important point that you have to grasp is the fact that photosystem 1 receives more light energy in comparison to photosystem number 1. So in other words, what you are expecting is to find more numbers of electrons generated from photosystem number 1 in comparison to photosystem number 2 in comparison to photosystem number 1. So what exactly is happening on photosystem number 1? We have spoken of the issues of photoexcitation. Yes, photoexcitation is happening here, and in the same vein, photoexcitation also is happening to your photosystem number 1. But now the question that we have is, this is a system that is working together so as to generate ATP at the end of the day. So when a certain process is going on, it should stimulate another process into happening. So now what we have here is that we are having our photons hitting onto our chlorophyll that is found in. Let's narrow it down right now to the issue of to our structure, which is our photosystem number 2. You realize that on the photosystem, it's a complex. There are enzymes that are found on photosystem number 1. There's an enzyme that is responsible for splitting of water. You still remember we touched on the issue of photolysis. So what is happening right now is light energy is hitting on the water in the photosystem number 1. The photosystem number 2, the enzyme that is responsible for splitting your water will do the following. So I've got a water molecule. It is receiving light energy. And we know light energy has heat. So the heat facilitates or defines our lysis, our breaking down of the water molecule into oxygen plus 2 hydrogen ions. Let's see whether this is balanced. You have got your 1 oxygen atom, so use it, and then 2 hydrogens. Yeah, this is what is happening. So right here, let's narrow it down just to photosystem number 1. What we are having is our thylakoid membrane. And what we have here is the stroma. And what we have here is our photosystem 2. What we have also here is another photosystem 1. Forget about the other details. We just want to explain what is happening in this particular instance. So what we have right now is we have broken down our water molecule into hydrogen ions, and these hydrogen ions are filling up our lumen. This is our thylakoid. This structure here is our thylakoid. Our thylakoid lumen, and what is involved here is our oxygen. And oxygen, of course, we know that is involved through those tiny walls that are concentrated on the outer surface of the leaf, known as the stroma. So what we are talking about right now is as electrons are moving, this is photoexcitation. We have just touched on the issue of photolysis, and now we want to concentrate on the issue of photoexcitation. As we receive more and more light on photosystem number 1, what is happening is we are going to push electrons and they start moving through the electron carriers that we have spoken about. And before we reach the other details, what we want to understand here is what is happening. And according to your physics, you understand that every time electrons flow, there's a current that is generated. Whenever electrons flow, there's a current that is generated. So we want to talk in terms of the electrochemical gradient and electropotential gradient. Okay, so what we're talking about right now is as more light is received by a photosystem, your electrons begin to move. And as electrons are moving, you remember the stroma, we say that it is filled up of liquid, and obviously when you talk of liquid, much of a greater percentage is water. You're talking of water. So there's something that happens as your electrons are moving, they are attracting, the current gives the energy that breaks away, because like you know, water is made up of hydrogen, which I can call them protons, hydrogen cation ions, and also hydroxide. So according to physics, we know that like poles, they repel and unlike poles attract. So what is happening is electrons are populating our membrane, forming what is known as the electron transport chain, because once the electrons start moving, what they create on our thylakoid membrane is what is known as the electron transport chain. And as that happens, the current generated is the energy that is going to pull off a proton. When I say proton, I mean a hydrogen cation ion from the water molecule. So at the end of the day, this is what is happening. We end up having more hydrogen cation ions, or you can call them protons, populated in our, this is now populated in our lumen. And then at the end of the day, this side has assumed a negative charge. And this charge is assumed a positive charge. And what we understand from chemistry is that when you have more hydrogen ions in a solution, that kind of environment is said to be acidic. This is so in our alumen, it is now acidic, and then this side is now alkaline. More hydroxide in comparison to the concentration of hydrogens in that region. So at the end of the day, in the same vein, because we're talking about the electropotential gradient, this is referring to our pH, and we have defined this environment as acidic and this environment as alkaline. And then we also want to look at it in terms of the electropotential gradient. As you can see, we have more hydrogens. We have got more hydrogens in our lumen in comparison to our stroma, and we shall get into how that defines the photophosphorylation at the end of the, after having considered all the other protein found on the membrane. So right now what we have covered is the issue of photosystem number 2. We need to get into cytochrome B6 core complex. Now you realize that a proton is a charged ion. So under normal circumstances, it cannot permeate the membrane. In order to get into the lumen, what it needs is a transport protein, and that is the function of cytochrome B6F complex. It is the enzyme that is responsible for pumping protons into our into our thylakoid lumen, and then moving on to photosystem number 2. What is happening on photosystem number 2 is that, like what we said earlier on, we alluded to the fact that if photosystem 2 received more light energy in comparison to photosystem number 1. So basically, the function of photosystem 1, we have seen that it is responsible for photolysis. So what is the major function of our photosystem number 2? As you can see, when we narrow it down just to these two structures here, you have got your photosystem 2 leading you to what is known as leading you to this transport protein that is known as the NADP plus reductase. And what I'm about to explain in detail are the intricate details surrounding the whole mechanism, how it works. So you will realize that, okay, maybe before we get to what goes on photosystem number 2 and NADP plus reductase, we need to understand, we say that as photons hit on chlorophyll, electrons are then liberated. But the question is, how do we replenish the electrons that are leaving our photosystem? And the same question applies also to our photosystem number 2. So you begin to realize that on photosystem number 2, the process of photolysis, we have electrons that were liberated. Those electrons are actually what is used to replenish the electrons that are coming out from your chlorophyll, so that the electron transport chain perpetuates. In the same vein, the electrons that are coming from photosystem number 2, as you can see this continuous line, are the electrons that are going to replenish the electrons that are coming out from the issue from photosystem number 2. So now we want to know what happens, because as you can see, this is the terminating point of the electrons. What exactly is happening? What's the function of photosystem 1? How is it different from photosystem number 2? You realize that photosystem number 1 is known as, it is responsible for reducing your molecule NADP plus, and you see how it is like that. So what happens here is that you have got your NADP plus molecule, which is the oxidized state of your NADP molecule, which is coming from, it's actually coming from the light independent stage. And now what happens is, like, when electrons are flowing through your photosystem number one, these electrons, so what we have is, there's a reaction that involves NADP plus molecule. As it is gaining these two electrons, it needs one actually to form a P, and then your hydrogen also that is in the stroma to form an NADPH molecule, which is an electron carrier. It harvests our energy that we need in our fuel. That is, at the end of the day, our glucose is our fuel molecule. We need to give it so much energy. Okay, so what is happening here? The reason as to why this complex here is called NADP plus reductase, is that as electrons are passing through the complex, as you can see from the first demonstration that I did, we are moving, oxidation states of these molecules are changing. We are moving from a +1 to 0. This means a decrease in oxidation state means reduction. That is the reason as to why this complex is called an NADP plus reductase. We have reduced our molecule. So basically, in a nutshell, the comparison between photosystem number 2 and photosystem number 1 is we have realized, but as for now we haven't. We have only realized the issues of photolysis, but actually there's another function that we shall get to explain about it. And then we have photosystem number 2. We have seen that it is responsible for reducing our molecule NADP and formation of our NH chorea known as NADPH, which is later used during the light independent stage. So let's move on to the next stage. What I'm just going to do is to simply read out some of the points from what I've been explaining. Visible light is part of the electromagnetic spectrum. Invisible light, as it were, has 7 colors. The color you see is what is reflected back, the rest is absorbed. So the green light that we have on the leaves is what is reflected. The other 6 colors are responsible for photosynthesis. And as alluded to earlier on, light travels in packets of energy that are known as photons. And then we move on to the concept that we alluded to earlier on, which is of photoexcitation. We need to know in step by step what happens is photons hit our chlorophyll. What happens is energy packets hit photosystems. Photoexcitations, photons hit chlorophyll in the photosystem. Photons have heat energy, and this should stimulate movement. Electrons from the photosystem begin to move, invading the photosystems. Movement of the electrons creates what is known as a current. Movement of the electrons is happening on the thylakoid membrane. Consequently, this membrane assumes a negative charge. More photons from light, meaning increase in photoexcitation. A series of electrons, therefore, are fired from photosystem number 2. More photons from light, meaning increase in photoexcitation, or the statement was repeated. The electric current powers the movement. The electric current powers the movement of protons from the stroma into the lumen of the thylakoid. Remember, unlike poles attract, electrons are carried and transferred by the electron carrier molecules. Cytochrome B6F complex pumps hydrogen cut ions into the lumen. This movement of electrons defines what is known as the electron transport chain. Moving on to the next slide. Okay, so this slide, this image basically explains the concept that I was talking about of the issues of when we have, this is our thylakoid membrane, and this is our stroma, and these are our water molecules populating our stroma. And then what we have at the end of the day is this that I was talking about. From this, our water is split, and where is the destination of the electrons? And from this equation, you can see that the electron, this electron was harvested into our NADP, our NADPH, which we need for building our sugar, that is our glucose. And in the same vein, we haven't touched on the, okay, we are still, sorry, I've forgotten to touch on the last, protein transport, which is the ATP synthesis. So from photosystem number 2, now what we have here is, there's another concept that we forgot to talk about, that's why it slipped my mind, which is known as the proton motive force. And remember, we touched on the issue of facilitated diffusion. So considering our transport proton ATP synthesis, what is happening here is we have a situation whereby inside our, let's go back to this, inside our thylakoid lumen is now concentrated of hydrogen ions, and what we have here are less hydrogen ions. And when that happens, you know, our environments, molecules, they want to exist in isotonic state. What do we mean by that? So in other words, these molecules will seek to reconfigure themselves, rearrange themselves in such a way that they are evenly distributed. So what happens is now we have electrical potential gradient that is defined. What we have here is we've got more hydrogens in the lumen and less hydrogen ions there. So in other words, according to the laws of diffusion, molecules will seek to move from a region where they are concentrated more to a region where they are concentrated lesser. So what then happens is that, but now the challenge that we have is they cannot permeate the membrane because they are charged molecules. So they need a facilitator, they need a protein transport to get them to the other side of the stroma. And that is how our ATP synthesis comes into play. And this is the reaction that is happening by the protein transport complex. What is happening is we have got our ADP reacting with a phosphate group, the hydrogen, to produce your ATP, which is needed for powering up the process for building up sugar building reactions. So right now what we have covered intricately is the details surrounding what goes on as far as the light-dependent stage is concerned. Let me see whether there is a summary. So what we have on this slide is basically one of the concept that we have touched on, the issues of the question of how is our oxygen, how is our electrons that are kicked out from our photosystems replenished. So this is what I have explained. Okay, let me just go through the presentation. PS2 and PS1 are losing electrons. How are the electrons replenished? And according to the equation there, you can see that this is two electrons that are discharged from the water molecule. So on PS2, electrons are replenished through the oxidation of water by photons, what is known as photolysis. And then increase in oxidation state is oxidation. So in other words, our water has been oxidized by the light. Our light has oxidized our water molecule. And then PS1 gets electrons from photosystem number 2. And that's the equation that I wrote on the board. And this process whereby we generate ATP is generated from this reaction is known as chemiosmosis, and ultimately our light-dependent stage yields ATP and NADP, which is needed for this synthesis of our glucose. Explain the ETC, giving the distinction between photosystem and photosystem number 1. We have already touched on that. And that is the comparison. I'm just going to read through what we've already touched on. photosystem number 2 is a strong oxidant, water oxidant. Photosystem number 2 is a weak oxidant and therefore a strong reductant. Photosystem number 2 absorbs more light, whilst photosystem 1 absorbs less light, and this defines the Z scheme of photosynthesis. The Z scheme of photosynthesis, as you can see, we are explaining in terms of the electropotential of the two. This one is firing more electrons in comparison to this one. Photosystem number 2 has a higher electron potential as compared to photosystem 1. Photosystem number 2 gives off more electrons than photosystem number 1. Photosystem 1 gives off ATP, whilst photosystem number 2, sorry, it's vice versa. Photosystem number 2 gives off ATP, whilst photosystem number 1 uses NADP. And what we have on the screen right there is the complete equation of what is happening during the light-dependent reaction, and we shall get to know the intricate details as we move on. But right now what I'm just going to do is to read that out. You've got 3 molecules of ADP reacting with 2 molecules of NADP plus 2 molecules of water plus 3 phosphate groups to give off 2 molecules of NADPH plus 3 molecules of ATP plus 4 electrons and 2 hydrogen as oxygen gas is liberated. That's it as far as the light-dependent reaction is concerned.